Yeah. Okay. So what I'm talking about is essentially I gave an advertisement about the occupancy models for for raptor and owl population studies. So these models are exactly 20 years old, have been invented, discovered in 2002 and by two different groups. And to me, they are some of the most powerful and but at the same time underutilized analytical methods in population studies, especially of raptor and owls, where I'm going to argue there that in raptors, perhaps more than in many other species, we have really territory or a site, which is a key conceptual unit in our population studies. And that even without banding, marking individuals, we can learn a lot from such territory occupancy data. However, at the same time, we have typical observation errors. We typically in our population studies, we have coverage bias, which may be random or non-random, the latter being called preferential sampling. We always have false negative errors. We may have false positives, and we may also have state assignment errors. And static or dynamic, so for 1 year or for 2 years or more, occupancy models, site occupancy models, they're perfect to analyze such territory data and to correct for some or all of these data. Now in my presentation, I give illustrations of the models only and pointers for more information. But yeah, so start with the key importance of a territory in raptor population studies. Look at these beautiful species here. This is a Malaysian peregrine falcon, by the way, photographed by our late friend Ui. Goshawk in Europe, sparrowhawk, bearded vulture, golden eagle, eagle owl, pygmy owl, barn owl, and as an honorary raptor, so as to say, the wonderful great gray shrike or northern shrike, as the Americans call it. What do they have all in common? They have territories. Where a territory can just be broadly defined as a site or in some kind by which these raptor and owl populations are often organized very strictly. So we have, there are more or less exclusive areas for nesting or wintering, and often they're highly traditional. In some cases, the same territory may be used for centuries even. For some of the falcons with carbon dating, this has been proven, for example. And often territories are associated with specific habitat features like cliffs or, here we go. Or buildings maybe, or in man-made stuff like nest boxes, but even for tree nesting raptors like goshawk or sparrowhawk and many others also all over the world, it has been found that relatively stable territory networks occur even in woodland or over time. So as I mentioned before, even without marking individuals, we can learn a lot biology from territory occupancy data, where population size is just the number of occupied territories. Population structure, we can distinguish, for example, sites occupied by single birds versus pairs. Population trend is the change over time in the number of occupied sites. Population trend then can be studied as a function of the factors that underlie the turnover, site colonization and site extinction. And we can study spatial temporal drivers of these population dynamics rates, so covariates which affect population dynamics. We can study competition by asking, for example, in the interspecific case, whether a site is less likely to be occupied by some species when another species is also present, or intraspecific competition we can study by asking whether a site is less likely or more likely to be occupied when a higher proportion of the surrounding territories are also occupied. We can generally study population regulation when we recognize the territories and the associated foraging areas at different qualities. So wouldn't it be great if there was a statistical model to study such territory occupancy data so that we could learn all these things? And of course, my main message here is occupancy models are the answer. But before we go to them, I have to look at some reality in the field, which are what's often called the observation process here in population studies, or measurement errors in bird population studies. Now, the observation process can be broadly defined as the process which maps what's out there with what we observe, our raw data. And it's composed really of at least 4 different types of sources of errors. for example, non-visitation errors, which is when not all sites are visited. This can be random or not. The latter, again, be called preferential sampling. We have false negative errors when we fail to detect the bird. Yeah. Okay. Yeah. So false negative errors when we fail to detect birds that are at the site that are occupied. False positive errors is the opposite. So if you go to a site that's not visited, and perhaps we see a mere transient bird and conclude erroneously that the site is occupied. And if we distinguish different states of site occupancy, we may see a single bird only, even though a pair occupies a territory. Now, all of these errors, they're totally obvious to us when we are birder or to us professionals when we're in the field. But unfortunately, they're all too easily forgotten and swept under the rug when we analyze our data in the lab. And this is not good, because ignoring these measurement errors will cause bias in almost anything we want to look at in our raptor population studies. So we can, depending on what kind of error we have that we do not account for, we may underestimate population size or overestimate it, and also like things like population trends or colonization extinction rates. So occupancy models, they let you analyze territory data in population studies, estimating all these cool things, while at the same time correcting for these measurement errors. And again, I'm not gonna show any math here about the models. You can read this up in many different sources, and I give some pointers to those. I'm just gonna say here that occupancy models or site occupancy models, that's the same. They can be called hierarchical models, which are a combination of two components. There's a first component which describes the true state of a site, of a territory, for example, presence or absence at the territory. And the second component accommodates one or more measurement errors. And depending on the type that you have, these models can give you estimates of all the above quantities of interest. At the same time, you can correct for all the measurement errors, or for one or multiple sources of measurement errors that we just discussed. And again, to say, to just drive home my main message of the talk, given the ubiquity of sites and territories in raptor population studies, occupancy models are the canonical analytical framework for such studies about population occupancy. So here I show, in a way, I give some examples of what typical data in raptor population studies may look like and what we can estimate from what kind of data. Yeah. So the very basic requirement for occupancy models is we must define some sites, here territories. Now, if we study these sites, if we study a population over multiple years, it's best if the territory ID is constant over years. So if at least some territories remain there or are visited over multiple years, then we must define the true states of a territory, which will be unoccupied in part, which will be unobserved, unoccupied versus occupied, which is the most common, or perhaps we may have occupied versus occupied single bird, occupied by pair versus unoccupied. And typically the data are collected during one or more visits to some or all of the sites in a population. And what you see here is all of this is really just the basic field protocol of most raptor population studies. So to give an illustration of the typical types of input data that we can use in such occupancy models, let's just dream of a peregrine survey in Malaysia. Look at these absolutely wonderful sites here, wonderful karst sites here. Can be fun to survey. These are my colleagues, right? Absolutely breathtakingly beautiful sites. This is my favorite site in northern Malaysia here. This one here with a pair here, and there was also another pair here on the other hump behind. But let's not get carried away by these wonderful pictures and get back to business. So here are some example data that we might collect in such peregrine survey, where we organize the sites, like the territories here, the known or suspected places where a pair could live in the rows, and then we give the result of our surveys here. Let's assume this is 2019. Here, this would be for the static single season, no repeat. So either we assume that we have no repeat visits, or we aggregate the information over repeated visits for the year. And we only distinguish a single state of occupancy. So we may site Pearlis 1 was not visited. Here, some sites were not visited. Other sites were visited and found to be occupied or found to be not occupied. We can code this in a different format. Non-visited sites, this is gives a not available, an NA, and we have a binary coding here for occupied and non-occupied. And here, these data allow us to estimate the apparent occupancy probability, ignoring perfect detection, and we can study covariate effects. So what governs whether a site tends to be occupied or not. We can have a similar, completely analogous scheme here if we distinguish multiple states of occupancy, for example, single birds versus pairs here. This then allows us to estimate the apparent proportions of occupied sites per state and study the covariates, for example, site quality or so, which determines whether a site tends to be not to be occupied by a single bird or occupied by a pair. Now, a very frequent scheme is here that we repeat our population surveys over multiple years, so we have dynamic or multi-season, multi-year data. Here, it's still assumed we have no repeat visits or aggregated visits and a single occupancy state. So here we show that we assume we have multiple years. Typically, we have, as before, some sites that are not visited in certain years. In some years, we may not be doing any field work at all here, and yeah, but we have at least some of the sites which are visited in multiple years, multiple successive years, and this is important here because these sites which are surveyed multiple years in successive years, they contain most of the information about the dynamics of the population. So here we see an extinction event. Site Pearlis 1 here was occupied in 21, but not occupied in 22, or site Selangor 2 here was not occupied in 21, but occupied in 22. Remember that these are completely imaginary data. I would have loved to do field work in Malaysia, but unfortunately I couldn't here. We couldn't due to COVID and other things. So this contains a lot of information about population dynamics. So therefore, we can use occupancy modeling, even ignoring detection errors. We can correct for coverage bias, not all sites visited. We can estimate, therefore, the total number of occupied sites under the assumption that detection probability is near 1, close to 1. We can also estimate proportions of occupied sites. And importantly, for multi-year data, which is probably the rule in raptor population studies, we can estimate trends, rates of site colonization and extinction, and we can explore covariate effects in all of this. What we cannot do is we cannot formally estimate detection probability or the probability of false positives. For this, to do this latter here, we need extra information. And the extra information may come in different forms, but the most typical extra information that allows us to estimate these error rates here is repeated visits. So let's look at the schematic of what kind of data we could get in a single year here for our imaginary peregrine survey in Malaysia, where we now assume that we have some sites which are occupied, some sites are not occupied, are surveyed or are visited just once, like Perak 1 or Pahang 4, but at least some of the sites here are surveyed, visited multiple times here. And it is these multiply visited sites which have a so-called mixed detection history. So where sometimes a pair or the birds are seen, sometimes they're not seen, which these patterns here and down here, where we have ones and zeros, detected and non-detected, non-detected, detected, these patterns here, they contain most of the information about imperfect detection, about detection probability, because under the so-called closure assumption that Pearlis was always occupied during the multiple visits here in the same breeding season, under this assumption, we can be confident that this zero here, this non-detection, means that the site, the species has been overlooked here. So these zeros contain a lot of information. Yeah. Likewise, if we have multi-state observations, again, so-called mixed histories, single bird visit seen on one visit, pair seen on the others, they contain most of the information about the state assignment errors. Next, I want to give you some examples of site occupancy models in action from some own work. I start with my favorite honorary raptor, the great gray shrike. This is just a hobby study in my birding on the weekends or on evenings and afternoons or something. 2 years ago, I conducted opportunistic surveys in 32 such sites, such winter territories, which are on the order of about 1 square kilometer. They are the sites shown here, and each column here shows 1 day when I conducted some visits. NAs means that the site was not visited on that day. 1 means site visited and great gray shrike found. 0 means site visited and great gray shrike not found. I observed shrikes at least once in a total of 14 territories, and my question here is how many sites were occupied and what's the detection probability of visit? I fitted the simplest possible site occupancy model here, where I found out the detection probability. Now, these are so-called posterior distributions, so they're a Bayesian version of they assess my knowledge or my uncertainty about these parameters. You can just treat them like any estimates here. So the highest point here gives you in a way your estimate of a parameter, and the spread, how spread out, how concentrated this distribution are. They say how certain or uncertain you are about this parameter. So my detection probability parameter estimated as 0.41, which means that if I go to an occupied winter territory here, I have only a chance of about 41% to actually see the shrike that's there. So 60 or almost 60% probability of missing the shrike if it's there. And therefore, if I correct for this, which happens automatically in the analysis of the model here, here is my estimate of the winter population size. The observed 14 sites is here. And I see that there's a lot of uncertainty here. It could be the confidence interval goes from 16 to 31. There's even a non-zero probability that all 32 sites are occupied, but my best estimate, the so-called posterior mean, is 23. So my best estimate is that I overlooked the shrike at a total of 9 winter territories. So this example shows that how I can correct for coverage bias, not all sites visited. I can correct for detection bias here because I have the multiple visits, and and come up with a rigorous estimate of winter population size. My second example is long-term population studies of goshawks in a study area in Switzerland, where they distinguished 3 states of occupancy. Well, unoccupied versus single pair versus pair. They had a lot of missing values at the beginning of the study, but also later on. Now, in the analysis, I only distinguished occupied versus non-occupied. And these are aggregated data, even though most of the territories were visited multiple times a year. I only have here the aggregated data, so I could not formally estimate detection probability, but I can still, under the assumption that detection probability is close to 1, I can still come up with a formal estimate of population size, so estimate these missing values, correct for coverage bias, and then look at the dynamics rates. So this is what is shown here. The observed population size are the open circles here, and correcting for sites which are not visited with 2 different types of occupancy models here represented by the different colors, I see that in fact the population probably has declined from about 15 pairs to only about 1/3 in the last years here. And looking at the dynamics rates which govern this change here, I see that the site persistence rate has not changed very much, has wobbled around a little bit, but interestingly, it's a site colonization rate. So the probability that the site which is not occupied in 1 year becomes occupied in the next year, this site colonization rate has steadily declined over the years, which may suggest that either the quality of the sites here has declined, or possibly that source population have declined. So what this shows, again, we can use these occupancy models to correct for coverage bias. And importantly, we can investigate possible causes of such a population decline. Very interesting, I find. This is an example which we just published in IBIS, and so because I'm always a little bit short in time here, I'm gonna crash over it a little bit. It's a similar type of data as we have for the goshawks. We distinguish unoccupied versus occupied. We have aggregated data, multiple visits to many, but most of the sites, but we only have the aggregated, so we cannot estimate formal detection probability. And we wanted to look at post-TDD crash recovery patterns in 5 areas here in the French part of the Jura and the Swiss part of the Jura. And you can read this up in the paper, or send me an email. I can send you the PDF. We again see quite important patterns in colonization, in persistence probability declines, in persistent probability declines, in colonization probability. These are the estimates of population size and the observed data in 5 regions of the subregions of the Jura. This is the Jura as a whole, where the observed data, these are the open circles, suggest an increase, but 2 different types of models, 2 different versions of the occupancy model show that we actually have had a decline over the last 20 years. So the top of the recovery, of the post-DDT recovery, has been around 2005. Well, beginning of the 2000, and since then we have had a decline. This is another example here, which shows, which illustrates multi-state occupancy models. So for the Eagle Owl national monitoring, if you like, they based on opportunistic surveys of the eBird type, where we have data from 0 to 20 visits to the same site for a total of 274 territories that were occupied at least once during this 10-year period here. This is the observed distribution of the Eagle Owl in Switzerland over a much longer time period, where there were a total of about 339 known sites. So this is from a book chapter here in our AHM2 book here, and shows again and goes into the issues of preferential sampling, of state assignment uncertainty, and how correcting for non-random site visitation bias or coverage bias, which is called correcting for preferential sampling, can lead to significantly different population trend assessment for the total population, for the number of sites occupied by pairs, that's the P, and for the number of sites occupied by single birds, this bit here. This is when we do assume that sites are visited at random, total population, pairs, number of single, and this is when we account for the fact that people have a tendency of going preferentially to those sites where they know that the species occurs, or where they assume that there's a higher probability to actually see the eagle owls. We can
yeah? You have 3 minutes, Marc.
Okay. Yeah. Thanks. Okay. So just a final note here, that the occupancy model, they're really a species, they're a specialized sort of species distribution model. You can download in an English version of a free English version of our last breeding bird survey here. And just to emphasize this SDM quality of occupancy models, also I throw some maps at you for raptors here in Switzerland. This is 300 kilometers from left to right. Barn owl, pygmy owl, little owl, horny owl, goshawk, red kite, kestrel. Fitting occupancy models in practice, there's a lot of free software and excellent software here. For example, Unmarked, and I was pleased to see that you have 2 workshops on the use of Unmarked for fitting occupancy models here associated with this conference, and that's very nice. Some general references on occupancy models are here. And again, I don't know whether my talk here is recorded, or you can get this. If you want this, you can send me an email and I'll send you a PDF of the talk. Then you have these sources. There's really useful internet groups and help forums shown here. And my take-home messages is really there's a ubiquity of the site in territory of the territory in avian biology. Most raptors and owls are highly territorial. And we can learn plenty of interesting biology having to do with territory and how they're occupied or not. But we have these 4 different observation areas, and occupancy models, they can give you estimates of all the territory related stuff, correcting for these observation areas. So to me, they are the most natural analytical method to learn about the population biology of unmarked raptors while correcting for these observation areas. There's a lot of free resources for fitting these models. So if you're studying raptors or owls in the field, learn occupancy models, start using them. And in the field, always record all sites visits, also when you see nothing. Thank you for listening again. Many apologies for having been late here. Yeah. Thank my dear colleagues in Malaysia for a lot of pleasure during our field work. And I also have to acknowledge all the anonymous photographers from whom I just stole their wonderful pictures from the internet. Thank you.